continuing with our preview of the whole course. Then in the second half of the course, we'll start by moving into an important economic question about the network we use every day. It's about your and my monthly bill from our internet service provider, especially a mobile wireless provider. For example, in the US, AT&T Mobility and Verizon Wireless, the two largest cellular providers in the country, in the last 1 to 2 years shifted from unlimited mobile data to a metered system where you have to pay based on how many gigabytes do you consume every month. And the current price is $10 per gigabyte. Now we know that it's conjectured Apple will release iPhone 5 that supports LTE. And a lot of people are looking at the potential impact on the amount of bandwidth each user will have to use, or more strictly speaking, the amount of capacity that a user will be using over a month. It's going to grow like crazy. And this $10 gigabyte may become a threat to the existing business models of many players in the ecosystem. So how do we adapt? And in fact, why am I being charged $10 gigabyte anyway? Why can't I keep getting unlimited buffets on my mobile data plan? Well, in some countries in the world, there's never been an unlimited data plan. And in some other countries, they are contemplating switching from unlimited to metered plan as well. And one big reason why the operator shifted gear is because what I call jobs inequality of capacity, in honor of Steve Jobs. Now, in 2007, with the introduction of the first generation iPhone, at that time the only carrier of that iPhone is AT&T, and AT&T saw a 55 times increase in its mobile data consumption very soon after the introduction of this wonderful new device. And this device, together with its app ecosystem, unleashed the dramatic growth curve of demand on mobile capacity, to the point where the supply of capacity per dollar of investment cannot grow at the same kind of rate. So mathematically, the first derivative of the demand curve exceed the first derivative of the supply per dollar curve much faster. And this is one of the reasons why the operators say, I have to switch to something, for example, like $10 per gigabyte. Now, whether it should be 10 or X dollars per gigabyte, there is something interesting and good about usage pricing, though. And we'll look at how we can understand the economics behind usage pricing. Along the way, we will introduce something called utility model, and how utility maximization by each selfish user can lead to interesting market equilibria. And this utility maximization and the idea of pricing as a signal to regulate demand and supply will be used at other time scales very soon in the course. Then question 12, we continue into something called smart data pricing. They try to provide a win-win between consumers, internet service providers, and content and app providers. Now, one of these smart ideas is so-called time-dependent pricing, TDP, which is useful not only for mobile or wireline networks, but also for transportation networks, for energy networks and smart grids. And the basic idea is that you are charged not just based on how much you consume, but also when you consume it. And with a proper pricing coordination, we can change the traffic profile of demands over, say, a 24-hour period from this kind of curve to the dotted line curve, where the differential between the peak and the valley becomes much smaller as we chop part of the peak and dump that into the valley. Now, we'll also see a couple of other smart ideas, including the so-called 1-800 number model for mobile data, where not only consumers get charged, but also the content app providers. We'll look at another smart idea where different prices lead to different products. Now, you may think, different products command different prices. That is natural. Why would you say that different prices will lead to different products? Well, it turns out that different prices will induce different demand behavior. And if the products are different depending on the congestion level, then that may create product differentiation. So we'll survey a few interesting ideas being contemplated by different carriers. Now, at this point, we will have talked about internet tangentially quite a few times, and it's about time to talk about internet design itself. And question 13 is, how does traffic go through the internet? Now, before we can address this question, we have to first understand some of the basic principles behind the evolution of the internet. The internet really is a loosely confederated network of networks. It is not a single network, but a network of networks. So one of the powerful principles behind this network of networks is so-called packet switching. Compared to the old circuit switching that governed, for example, our old telephone network, packet switching tend to be more efficient. It provides an economy of scale, and it provides a more efficient resource allocation, just like CDMA versus other types of earlier generations of cellular network. Instead of dedicated resource allocation, you do shared resource allocation. We look at packet switching. We also look at the idea of layering, which is really a modularization of a large complex system like the internet into different functional modules. For example, this picture is a typical 5-layer reference model. We'll look at the different functionalities executed by different layers, and we'll look at what does it mean to say that there is a boundary between two layers. And then we look at the third principle of overlay network and spatial hierarchy. Now, with those three big principles of the internet design behind us, we then will come back to routing, which is carried out in this layer by the IP protocol. Okay, we'll look at routers, routing protocols, and forwarding mechanisms. Along the way, we'll also look at interesting network optimization problem and the solution through methodology called dynamic programming. And then question 14, we'll look at a solution that resides in the transport layer. The question is, why doesn't the internet collapse? Now, we know that on the longer time scale, as demand exceeds supply, you can try to increase supply, or you can try to regulate demand with pricing. What about a much faster time scale? For example, sub-second time scale. A link may get more demand than there is supply, and you can add capacity or change people's monthly bill on a half a second basis. Then what do? It turns out that so-called TCP, which is a protocol in the transport layer, has a congestion control mechanism. It is a distributed way to allocate limited network capacities among competing users, situated in different spatial locations. And we will look at the powerful idea of using pricing as a negative feedback signal. In this case, in the network with a fixed given routing and topology, and a very much faster time scale than what we talked about in lectures 11 and 12. And then we'll spend several lectures talking about two major trends in the technological networks today. Now, one is massive amount of content distribution, whether that's content generated by you streaming on Facebook, or there's content generated or licensed through Netflix. And coupled with that is the proliferation of video services on the internet, both wireline and wireless. Now, the first solution idea we looked at is so-called P2P. You may have used Skype, you may have used BitTorrent or PP Live, and question 15 is, why can these be free? Now, part of the reasons might be the digital rights issues, but part of the reason is that they are all P2P technologies. So when you add as a peer to the network, when you demand resources from others, you also contribute your resources. For example, if you are node A, you may contribute your upload capacity to help other nodes, say peer B and peer D. And we'll look at different ways for P2P networks to scale itself up. Because the key issue here we're facing today is how to scale up. And we'll see a powerful scale up property in P2P system. And question 16 goes into the other side of the coin, which is so-called cloud services, especially so-called rented cloud. Instead of, again, dedicated resource allocation, we do shared resource allocation. In this case, sharing data centers, which are the hardware components of a cloud service, whether that's Google's, Amazon's, or Apple's, or Microsoft's clouds. And we will see how data centers can scale themselves up, okay, to billion-dollar infrastructure in a gigantic building with 500,000 servers in there. Okay, we will see how we can scale up the operation of this shared facility by scaling out. What do we mean by scaling out? Again, the details in the lecture, but in this preview, suffices to say that we will build a multi-stage switched network, which is actually, perhaps ironically, dates all the way back to the early 50s in the study of telephone networks. How can we scale up the old telephone system? And we'll look at classic result by Cloche in what's called a Cloche network. This actually is a Cloche network, and we'll spend quite a bit of time just dissecting this picture. But one thing is obvious. You've got 1, 2, 3 stages of small switches, and you've got a lot of connectivity. All these blue lines provide a rich connectivity pattern. And the message is that not only capacity is a resource you want to allocate carefully, but connectivity, the patterns of who's connected to whom, is also a very precious resource you have to carefully manage. And then question 17 is on this video thing. Okay? Whether it's IPTV. This is a picture of IPTV architecture cartoon, or video over the internet, such as Hulu, okay, or Netflix, or YouTube. You may wonder, how can the internet provide the support for something like a video service? Doesn't video service require a lot of qualities of service, such as bit rate for playback, delay, variance of delay, and so on? And in lecture 13, we'll appreciate that internet does not provide a quality guarantee. It only provides a robust and cheap connectivities. Well, it turns out that you can then take those connectivities and add on top a variety of mechanisms to support qualities of service in video services. And then as we move into the final chapters of the course, we will go back to wireless. Question 18 is one that some of us must have puzzled with. Now, we all use Wi-Fi services. Wi-Fi, unlike the cellular services, use so-called unlicensed spectrum. You don't have to pay for the spectrum, but you don't have a large distance transmission or strong mobility support. Now, what's bothering a lot of people is that when you use Wi-Fi at home, okay, unless your home is in a very densely populated high-rise building, okay, then you face a similar problem coming up. But if you use, say, a single-family home in the suburb, the Wi-Fi speed is great. Okay. In fact, if there is a problem, it's often the backhaul away from the Wi-Fi access point, rather than the connection between the access point and your phone and tablets. But when you use it at a hotspot, the coffee shop, okay, hotel, airport, somehow the speed goes down, unless it's the middle of the night and there's no one else in that airport terminal. Okay? So somehow it says that Wi-Fi's interference management does not scale very well. And indeed, unlike cellular network back all the way to question 1, where we looked at a cellular network using power control, okay, control people's volume in the cocktail party, Wi-Fi use what's called a random access. This is a very distributed way to do scheduling. Who get to talk at what time rather than at what volume. And we will see that random access has many smart ideas in it, and yet still, in general, it faces a very difficult time in scaling up its efficiency as we go from just a few users to, say, a dozen users. So in other words, the tragedy of the common issue, the negative network effect, cannot be readily internalized or mitigated by random access and Wi-Fi. Now, speaking of your speed on the wireless devices, I don't know if you've done this kind of experiment. Try to download a large PowerPoint attachment on your mail application on your smartphone, and then divide it by the advertised speed by your operator. I don't know about your result, but I try this a few times, and often on a good day I get 3.7%. Now that means somebody somewhere took 96% of what I paid for away from the speed that actually I can use. Where did that go? Now, question 19 will be addressed by looking at non-ideal network conditions as well as control overhead. Now, we'll get to appreciate that operating a large, complex engineered network requires a lot of management overhead. Okay, and we'll see where the management overhead situates itself. For example, in an LTE 4G network, from the base station to the backbone IP network and across what's called a cellular core network. Every step of the way, there could be a weak link or node. Every step of the way, there's a need to run some control overhead. And they add up to take away a big chunk of the speed that you think you would be getting. In other words, the question, what is the true speed on my wonderful wireless device, is a question that has to be qualified with what, when, which layer, and for what application. Okay. And the very last lecture of this course will raise a question that we will have touched upon by then many, many times in both social economic network and technological network, and that is the question of what is fairness. Okay? Is it really fair to say that this way of allocating resources, which gives my neighbor's iPad a much faster download than mine, is that really fair? How do we quantify and make arguments about fairness meaningful? And we will see a few examples, including an example in the implications of tax rate in the United States. Now, if you actually understand what I have been talking about over the last 35 minutes of this preview, then you probably are overqualified to take this undergraduate course. Okay. But if you think you're interested, but you just don't understand all those terms I used, then wonderful. Okay, let's get this journey started together. And before then, let's talk a little bit about pedagogical approach behind this journey of 20 questions that we're going to be embarking momentarily. Because it is important to teach all the fun associated with these questions being formulated and at least partially answered in a way that is not too boring.